Everything's fine. You're seeing it correctly. Thank you, David. All right. Thanks again. So and welcome to JPEG-xs, balancing video compression and eye visual fidelity. I'm Andre Testa, and with Alain Champenois, we will be your presenters. So this track will cover the methodology we take to make the proper quality assessment on the compression algorithm. But first, I will give a real quick background about the overall effort. So once ST2110 really started picking up momentum in the broadcast and media industries, AIM started the ProAV working group. And the idea here was to leverage the work already accomplished and build on it by incorporating features specific to the ProAV market, calling the effort IPMX. As I said earlier, now we will focus on the video compression, but there are many others, as Andrew mentioned in his presentation this morning. So let's start by talking about the infrastructure we rely on. The current network IP infrastructure already offers many benefits for audio and video transports. IPMX wants to capitalize on those benefits to keep the installation cost down and also keep the installation easy. So what are those benefits? Scalability, supporting a wide range of installation from few devices to many hundreds. Simplicity, being very mature, it is well understood. It's easily configurable and manageable. Reusability, supporting many different use cases like KVMs and controllers, to name only those couple. ST2110 is built on a very common and widely used protocols, targeting existing Cat5e and Cat6 cables so that current setups can be leveraged. Let's see what kind of bandwidth is required to transport our video streams. As SD resolution clearly fits in a gigabit Ethernet network, as soon as you hit HD60, 444, for example, you already start seeing huge increase in bandwidth demands as it reaches 3.7 gigabits per second. UHD, 15 gigabits per second. 8K, almost 60 gigabits per second. It keeps increasing at a phenomenal rate. And now keep in mind, all these numbers are based on 60 Hz refresh rate. So now if you want to support HFR, for example, high frame rate, those numbers are just going higher. The word exploding comes to mind. So this is just to demonstrate that for economical reasons, video compression becomes a necessity in certain cases. Deciding to rely on uncompressed video imply a huge infrastructure cost because the equipment to support such bandwidth is very expensive. So it might be okay for some installations, but that is not acceptable to everyone, and certainly not for a big part of the ProAV installations. So this is why IPMX has made the support for a compression algorithm critical and one of the first items to address in its roadmap. What are we looking for when adding video compression into the equation? Preserve quality. The fact that video is compressed for transport reasons must not affect the user experience in any way, and certainly not visually. So therefore, we're aiming for a visually lossless compression. No latency, kind of self-explanatory here, but often compression is associated with added latency. IPMX specifically targets ultra-low latency algorithm. Simplicity. And this means more than ease of implementation. It also means like low power consumption, less complexity, less calculations. Multi-platform can be implemented in a variety of setups, whether it is on a CPU, a GPU, an FPGA, or ASIC implementation, giving you the flexibility to build either an hardware or software solution. Future-proof. We need to have provision for expansion. We know resolution will increase, bit depth will increase, HFR support, like mentioned earlier, HDR support. So these must always be kept in mind because the reality is constantly evolving. Open standard, this is integral part of the mission of IPMX, right? Promoting open standard solution. And ST2110-22 is defining the rules for transporting compressed video in ST2110 workflow. So to be part of IPMX, the transport of compressed video must comply to this specification. All right, so we determined the need for a compression algorithm in order to use the existing network IP infrastructure. We know what we're looking for in a compression algorithm. Next is, how do we determine that the chosen codec meets the needs? At Matrox, we have gained much experience internally on codec analysis. So we developed from ground up a H.264 codec. So we have tremendous expertise, and we obviously rely on it. We have in place a rigorous verification system and highly trained eyes to identify artifacts and flaws. This is mainly what we intend to cover in the remaining of this track, the methodology we use to make a clear assessment on image quality. And to do so, I have with me Alain Champenois. He is at the center of this effort at Matrox. So now, please, Alain, guide us through the main topic of codec evaluation.
Thank you, Andre, for your introduction. So let's switch. Here you go. Okay, so I'm Alain Champenois, and we will now explore how JPEG-xs compression works, its impact on visual quality, and how we can evaluate it. JPEG-xs implement a wavelet-based image compression pipeline, transforming an input image into a code stream. This pipeline, shown in the diagram, is composed of three main stages. First, we have a discrete wavelet transform. This stage transforms the information from a spatial domain in pixel to the frequency domain as wavelet coefficient. This stage only transforms the input data. It doesn't really compress and have negligible impact on quality since it's reversible. Next is the quantization stage. Using directive from the rate control module, the wavelet coefficient bits are reduced. This reduction of bits is obviously done at the expense of quality, which can create specific type of artifact that we will talk about later. Finally, we have the predictive entropy coder. This final stage will further compress the data to produce the final code stream. This is a lossless compression step, so it has no impact on quality. Note that JPEG-xs support a programmable quantization table, which prioritizes the bit distribution across the wavelet coefficient. This table can be optimized by the user depending on the content or the viewing condition to achieve better visual quality. Now let's see how JPEG-xs rate control allocate bit across the output code stream. So JPEG-xs is an intra-frame codec, which means that each frame is compressed independently with its own bitrate. Intra-frame coding has many advantages like simplicity for the implementation, low latency, and error resilience. JPEG-xs further partition each frame into slices, which in IPMX standard are going to be the width of the image by 16 lines. An important point to note is that each slice has its own target bitrate, derived from the frame target bitrate. Having each slice with a similar bitrate is needed to guarantee a fixed low latency. So from this data partitioning, we can determine that JPEG-xs, if you have a static input, you will produce a fixed quality output, each frame being identical. We can also say that within a frame, quality may vary between slices, a complex slice having more artifact than the simpler one. Also, the full content of a slice determines its quality, which means that a complex content on one side of the slice may actually impact the quality of the data on the other side of the slice. Now, let's talk about compression range for JPEG-xs. Visual quality is, of course, directly related to the amount of compression we use. JPEG-xs is a mezzanine high-quality codec, And different type of metric and measure can be used to describe its compression level. We have a BPP, which stands for bit per pixel. This metric has some of interesting characteristics, which make it very suitable to be used with JPEG-xs or other type of mezzanine codec when talking about quality. First, BPP is a simple float number that should stay between 1 and 10 for mezzanine codec. Secondly, BPP is independent from the frame rate, the resolution, and it will also abstract the bit depth and chroma type. This means that for a given BPP value, you should achieve similar level of quality across any type of format or resolution. So this makes BPP a simple metric to use when talking about quality. The two other metrics that are also used to define compression are the compression ratio, which represent the ratio between the input size and the code stream size, and the compressed bit rate, which is the final code stream size. We can see in the table how the BPP relate to those other compression metrics. Please note that for the bit rate, we only mentioned the video code stream size. So you need to account extra bits for the Ethernet IP protocol and any type of error correction that you want to add. Now, in terms of optimal compression, we can say that JPEG-xs will achieve good to visually lossless quality for BPP ranging from 2 to 8. And we will see later that the exact value of the BPP will actually depend on the type of content that you want to compress. Sorry. Now let's examine how visual quality is assessed for codec. We have two types of assessment possible. We have objective assessment, which use model to mathematically compute and calculate a quality score. This type of assessment can be done on a large scale and provide a uniform scoring method, which make comparison easier. Objective metric, however, are limited by how good their model are at representing the human visual system. Then we have a subjective assessment, which is done by a human viewer, which gives his feedback. As the name implies, this assessment will be biased and influenced by the personal knowledge, taste, and opinion of the subject. So these two assessment methods can be further classified based on the availability of the original input. In a full reference scenario, the input source is used and compared with the compressed output. This is the preferred scenario since it would give us the most accurate evaluation. The two other scenarios are reduced reference and no reference. These scenarios are normally used in a real-time environment by the receiver to detect any type of real-time transmission or encoding error. Now let's talk about the different type of metrics, objective metric we have. The two main most common family of objective metric are PSNR and SSIM. PSNR is a generic measure of signal distortion, and simply it calculates the absolute error introduced for each pixel of an image. Some variant exist to better represent the human visual system, but PSNR remain a crude and very simple metric. SSIM is a more complex model using luminance, contrast, and structure to compare similarity between two images. SSIM and its mini variant much better represent the human visual system. As we can see in the example, we compare PSNR and SSIM score for 3 distorted images. And as you can see, the PSNR can be easily fooled, unable to distinguish between the 3 types of artifact, while SSIM is able to score the best image. Note that PSNR and SSIM are primary spatial metrics, but they are often used in video analysis by simply averaging the score obtained for each frame of the sequence. We also have another type of artifact, which are temporal artifacts. And those artifacts can also appear in intra-frame codec. For example, having a flashing pixel between several frames. These artifacts are not detectable using the common image metric that we just talked, which are PSNR and SC. Therefore, to tackle temporal quality, a new objective video metric has been developed over the year, but they all had very limited success. Recently, a promising new video metric called VMAF was developed in cooperation with Netflix. VMAF used AI and machine learning to train its model in choosing the best method to analyze each type of content. Development of video metrics remain an ongoing field of study, even today, requiring an order of magnitude more processing than image analysis, and still not achieving the same level of accuracy. Now let's move to subjective assessment. Subjective assessment can be quite simple. Show someone an image or a video and get his feedback. However, to get a useful and comparable result in an efficient manner, over time, different types of methodologies have been developed and standardized to do subjective assessment. Some popular methods include single or double stimulus, where the subject gives his rating from bad to excellent or from 1 to 10, without or with seeing the reference. We also have forced choice and similarity judgment, where the subject gives his rating or choice between a pair of input, one of them being possibly the reference or the source. As you can expect, doing subjective assessment can be expensive, tedious, and time-consuming, normally requiring large number of participants working in a specialized and controlled environment. Normally, to achieve best result, you want to mix both subjective and objective metrics, but it's important to note that the best assessment method will heavily depend on the type of content and artifact you expect to encounter, which brings us to the visually lossless quality. Visually lossless describe a form of compression where, while the compressed data is different from the source, the difference is not detectable by a human observer upon close inspection. Mezzanine codec, like JPEG-xs, normally target visually lossless quality. For this type of level of quality, a special subjective methodology has been developed, namely the flicker test, which consists in rapidly alternating between two images, the reference and the compressed image. Any detectable visual change of the image will appear as a blinking effect, and therefore allow the user to pinpoint a difference. For the objective metric, the simpler PSNR metric become quite efficient at analyzing visually lossless condition because of its extreme sensitive scale. Note that for visually lossless codec, most of the analysis can be done on individual image, since without any detectable spatial artifact, a temporal artifact will become nearly inexistent. Now, let's see what type of artifact JPEG-xs quantization can create. For this example, we exaggerate the artifact by forcing a very low BPP value outside the range of effectiveness. Therefore, it's normal that you will be able to see them. So we can categorize the artifact in three main categories. First, you have the ringing and aliasing artifact, which happen with around high frequency codec content, with sharp transition. For example, black and white text. You will see ghosting effect or staircase effect. Second category of artifact are blurring or posterizing, which is a loss of detail or color happening with medium to low frequency content being removed. Final category is blockiness, which is an extreme type of artifact, which will happen when the codec start showing slice boundaries or pixelization of the image. So those are really the general category of artifact we can see with JPEG-xs quantization. But obviously, those artifacts will depend on the content type and the compression level you are using. Now let's talk about content, since content play a big role in how compression works. We mentioned before that compression effectiveness and visual quality is dependent on the content, and we classify the content in three main categories. First, we have natural content, which encompass everything captured with a camera, converting analog information into the digital one. This category covers a mixed range of content frequency, but exclude true high frequency content because of the discrete way the input was captured. Natural content is usually resilient to compression artifact and will produce good result even at lower BPP. So starting at 2 and more, you should get good, either good or visually lossless quality. Next category is graphic content. Graphic content is generated by computer generated graphic, which cover any type of content that is used as overlay or for animation. This category has more high frequency content than the previous category, natural. But because of the blending and other type of rendering manipulation, the edge transition are usually soft, and therefore graphic content usually don't have very high frequency information. Graphic content will usually have a good resilience against compression artifact and will give correct to visually lossless quality with a PPP of 3 and more. Last category is desktop content, which encompasses any type of pixel-aligned computer-generated content. This category has the highest frequency content, making it very simple to compression and more easily producing visually detectable artifact. This type of content requires higher BPP, 4 and more, especially for the more extreme synthetic case. So to put to trial JPEG-xs compression and see its impact on visual quality, Matrox did several evaluations, both objective and subjective, including synthetic use case and codec breaker scenario, to really understand the range and limitation of the JPEG-xs codec. From this work, we created a simple subjective visual demo with the goal of letting anyone experience how JPEG-xs compression works. This demo runs directly from a web browser using simple JavaScript and is controlled by a few keyboard keys for navigation. The demo includes every type of content we discussed and is encoded in a wide variety of BPP value using Matrox JPEG-xs encoder. Beside the reference and compressed image, the demo also includes a PSNR-based heat map that will show the difference for every compressed image. This heat map allows to more easily spot region of interest and also see the impact of compression depending on the BPP value. For testing, the demo supports the flicker assessment method, which allows the user to compare the reference and the compressed image, but also allow for comparing 2 compressed images or even 2 different heat maps. With this type of testing, it became very straightforward to analyze JPEG-xs quality and to determine at which BPP the data become visually lossless. So to conclude, using methodology described in this presentation, we at Matrox concluded that JPEG-xs quality is a good fit for IPMX ProAV market, achieving the desired compression target while staying visually lossless. However, you don't have to trust us. You can see for yourself and make your own evaluation by checking out our demo. Contact us by email for a direct link to download the demo, which is about 150 megabytes. So this concludes my part. Back to you, Andre.
All right, so thank you very much, Alain, for this very interesting information. With this demonstration, Alain showed us how JPEG-xs clearly has its place in IPMX in terms of image quality. And as a side note, I can add that to ensure interoperability between vendors, VSF is currently working on a technical recommendation, which is describing the transport of JPEG-xs video in the ST2110-22. Just another step to make sure integration of new components in the standard are well done. So that concludes our presentation. We sure hope that you found it interesting and you learned a thing or two about video compression algorithm, evaluation, and appreciation. Thank you very much.
Guys, before they leave, anybody have any immediate questions you want to ask?